Okay, we're going to go through our 7.1 notes today. We're starting the randomness and probability section of the book. Alright, chance behavior is unpredictable in the short run, but has a regular and predictable pattern in the long run. So think about when you're flipping a coin. Well, if you're only going to toss it 3 or 4 times, you could get 2 out of 2 heads, you could get 1 head, you could get 0 heads. When you're only tossing it a few times, you're not sure what probability you're going to get. That's why you usually only get 1 chance to win the lottery. But if I toss that coin 50 times, I'm more likely to be near 25 heads, maybe 24. If I toss it 1,000 times, I'm going to get closer and closer to that 50% mark. Because even if I'm not right on 500 out of 1,000, 502 out of 1,000 is a percentage that's really close to 50. Where when we're only doing 20 tosses, 11 out of 20 is not as close of a percentage to 50% as like 502 out of 1,000. So even if you're not exactly right on that center point, your percentage is getting closer and closer to the expected percentage of 50%. And that really just explained example 1. As you increase the number of tosses, your percentage is going to get closer and closer to the expected probability of 50%. Something is random if the individual outcomes are uncertain, but then there's a regular distribution after a large number of patterns. You don't know what number you're going to get when you roll a dice, but if you roll it enough times, you can expect how often you get certain numbers. Probability is a number between 0 and 1. 0 would be it never, ever happened. You cannot get an 8 when you roll a 6-sided dice. There's a 0% chance of that happening. And a 1 would be a 100% chance, because 100% is 1 as a regular number. If you roll a regular 6-sided dice, you will get a number. That's a 100% chance of happening. Something that happens 50% of the time, half, 0.5. I roll a 6-sided dice and I get an even number, because there's 3 evens and there's 3 odds. And mathematical probabilities based on imagining what would happen if you did it indefinitely. If you flip that coin infinitely many times, the percentage will be 50%. Okay, so probability theory was actually developed out of gambling because they wanted to figure out a fair value of bets of games of chance. People who were setting it up wanted to make a little bit of money, but the people who are playing have to make a little bit too, otherwise they won't keep playing. And we'll get to a little bit of the gambling theory later on. So, if you were on vacation 100 miles from home, would it be unusual to run into somebody that you know? And the answer is no, that would not be unusual. That would be almost expected. Yes, it's 100 miles from home, and who knows if you're there, but think of all the people that you know, all the people that your parents know, everybody they've ever went to school with, everybody they've ever worked with, all their kids' friends. You know a lot of people. And to run into any of them, not that unusual. Now, if I change it to say, would you run into your neighbor that you had when you were 2? Much more specific. Much less likely to happen. Then we have a law of averages. If a family has 4 girls, then according to the law of averages, the next child has a greater probability of being a boy. That would be false. Each individual child has the same chance of being a boy or a girl. No, it's not exactly 50%, but that's a whole biology lesson for you. It doesn't matter how many girls you had, your next kid is the same chance as being a girl as the first kid was. How about hot hand? Basketball player makes several consecutive shots. Is he more likely to make the next shot? The answer there is no again. Professional basketball players have stats. Each free throw has an individual probability on it, depending on each basketball player. If he makes 8 out of 10 free throws, each free throw he has an 80% chance of making, whether he's made the last 4 in a row or not. Which set of coins is more likely to occur? 3 heads in a row and then 3 tails, or head, tail, head, tail, tail, head. Those are equally likely. They're both 6 coin tosses, and they're both specific. Notice they both have 3 heads and 3 tails, and if I would have asked, compare this to just having 3 heads or 3 tails, it'd be different. But that specific order has the same likeliness of happening. Okay, probability. People often use probability to determine their risk. So some people refuse to fly because they think the probability of an accident is too high. Experts use probability to describe the risk of an unpleasant event. So flying is actually safer than driving based on percentage of accidents and deaths, but we seem to ignore that data. We worry about risks that almost never happen, ignoring some that are much more likely. And why is this? Because plane crashes are publicized. In plane crashes, everybody hears about it. And you're like, oh man, everybody on that plane died, so it's 100% chance of death. But how many planes are flying throughout the day, through the year, and people die in a car crash, and only the people who knew them even know about it. Another example of people ignoring evidence. Shark attacks. Think about how many people are swimming in the ocean and get attacked by sharks, and then people actually refuse to go into the ocean because of that minute percentage of people. Okay, lightning strikes. People are really worried about that at some points, but the actual values are really low. The people who get injured from lightning strikes. Alright, and simulation. We did a simulation yesterday with the Hershey Kisses. You can also use a random digit table, a calculator, or a computer software to imitate chance behavior. So like if you're flipping a coin 100 times, you don't actually have to flip a coin. You can use your computer to do that for you. Alright, the simulation example, we're going to do this in class. It is the airline hiring thing. If you're at home, instead of the beads, get out, I don't know, find something that you have 2 different colors and you have different amounts of. The directions are all at the top. And then we're going to simulate whether these women should have been or could have been hired by chance, or was it chance or was it bias? And then back to this. 2 random phenomena are independent if knowing the outcome of one does not change the outcome of the other. So, especially coin toss. You flip a coin toss, you get a head. The next one, you still have a 50% chance. If you get 3 heads in a row, you still have a 50% chance of getting a head. If you roll a dice and you get 5 fives, awesome. Your next roll, you still only have a 1 out of 6 chance of getting that next 5. Okay, those are independent. Something that's not independent is if you're picking like marbles out of a hat. If I had 3 marbles in there, all different colored, and I pick the red one out, well, my chance of picking a red one out now is not 1 in 3, it's 0 out of 3. Actually 0 out of 2, because there's only 2 balls left. Those would be dependent events. So independent events are not influenced by previous happenings. Okay, so we're going to do that hiring simulation in class, and hopefully you can find something to help you do it at home, and we'll talk about that